Good afternoon, everyone. Welcome to the online interactive session on network security and management. So today we'll have a brief discussion on the MAC based on block cipher, public key cryptography, the requirement of public key cryptography. So coming to the MAC based on block cipher, in this section we will look at several MAC based block cipher algorithms. Initially, the CMAC stands for the Cipher-based Message Authentication Code. So in the previous class, we had a discussion on the hash function as well as the MAC functions. So the main difference between the MAC function and the hash function was hash function does not use the secret key, and the MAC function takes the secret key to produce the tag or the hashtag or tag with the authentication code tag, for which we are going to attach to the message and for which we are going to transmit. So in this CMAC, that is cipher-based message authentication code, this code of mode of operation is for use with AES and DES algorithm. First, let us consider the operation of it. So the CMAC uses a key value to encrypt the encryption algorithm. For the encryption algorithm, the key is divided into two sets of the key 1 and the key 2, and the information has been given to the algorithm. So before giving the key value to the algorithm, the message is divided into number of blocks. So according to the requirements of the algorithm, according to the bit size of the message part plain text, the blocks is given to the encryption algorithm and the key value, and it produces the ciphertext. The same process goes out over here. So the message is divided into n blocks, and each n blocks processed separately with different key value. If the mode of operation is AES, then each block is divided into 128 bit. So if the mode of operation is 3DES algorithm, then your message will be divided into 64 bits of information. So this is about the message division of information into blocks, and each blocks will be processed separately. So each block of the plain text is given to the encryption algorithm with the key value K. So if your mode of operation is AES, then the key value will be either 128, 192 or 256. So if your mode of operation is of 3DES, then the key value will be 112 or 168 bit of information. So overall says here is in the CMAC algorithm, we are going to divide our information into number of blocks. If it is of AES, it will take 128 bit. If it was 3DES, it will take 64 bit. And each block of operation encryption algorithm takes also input as the key value. If it is of AES, it takes 128 or 192 or 256. If it is of 3DES, it takes either 112 or 168. So by taking these two information, the encryption algorithm encrypts into the ciphertext, and it will give for the next process, or it will transmit. If it is of the final part of it, it will declare it as a hash code of it. In the CMAC operation, as the message is divided into different blocks, the output of the first message encrypted, which has been XORed with the second message M2, and then it goes on for all the message till where it has been transmitted. Till where it has been divided, the message has been divided. So for example, my information is divided into 5 blocks. So the first block of information is being encrypted. The output of that ciphertext is been given an input, is being XORed with the second block of your plain text of message 2. And after doing the XOR operation with the message 2, it has been given to the encryption algorithm with the key value. It produces the output. The output of this second message will be XORed with the third message, and that information will be given to the encryption algorithm. That has been explained in this pictorial representation. That is, your message has been divided into different blocks. So each block has been given to the encryption algorithm with the key value. So it produces a ciphertext over here, hash code over here. This particular information is being XORed with your message 2. that is your plain text message. Once it gets the output of this, will be an input to the encryption algorithm with the second set of the key value. The same process goes on for the last round, for all the rounds till where it has been divided the information. And for the last round, for the last message, it has been XORed with the key value called K1. Here we can see here at the last round, your information is being XORed with your plain text message as well as with your K1 message. So this key is being given as an input for the XOR operation. The output of this will be given to the encryption algorithm with the set of key value, and finally it produces the hash code over here. That is what the last message is also XORed with the key value K1, and the message will be given for the final output, and that final output is called as message authentication code or a tag. So if the last message is not up to the B bit length, so that is, if my information is of the AES, then they say that the message has to be divided either 128-bit or 160. So if in that case, the B value will be 128-bit. For the last message, if it is not 128-bit, then we are going to use a concept called padding. That is where I'm going to add 1 and continuous 0 to satisfy the B bit length. That is to satisfy that the message should contain the 128-bit of the length of it. So if the last message consists of the padding concept, then it has been XORed with the other key value called K2. Same thing has been explained over here. So you can see here the message has been given to an input for the encryption algorithm with the key value. The same has been now XORed with the second plain text, and which has been inputted to the encryption algorithm. Same process goes on here. For the last message, you're going to do a padding concept over here, where you're going to add 1 and continuous zeros to satisfy the B bit length over here. Then you're going to do the XOR operation with the other set of K2 value. So if the padding concept has been done, then the second key is being used with an XOR operation. It has been given to the encryption algorithm with the key value, and it produces the hash code over the MAC code over here. So if the padding concept is not done over here, you're going to add a first key value, and then you're going to XOR, and then the same process goes out over here. Now, how this K1, K1 and the K2 are generated? So these K1 and K2 are generated from the key value itself. That is from the same key value from which we have been selected. So the block cipher has been applied to the block that consists entirely of the 0-bit. So the first sub-bit, that is the K1, has been derived from the resulting ciphertext, and by doing the left shift of 1-bit operations. After doing the left 1-bit shift operation, that has been XORed with the constant value depending on the block size. Whatever we get the value, that value we are going to say it as K. The same process, the same derivation goes on for the second key value K2. That is, first we are going to take a set of 0 bits information that has been given to an encryption for block cipher encryption part of it. Then we are going to go for the left shift 1-bit operation of it. Then we are going to do the XOR operation with a constant value. That constant value will be predefined there itself. Based on that resultant output, we are going to determine the K value, K1 value and K2 value. Second is CCM mode of operation. So that is counter with cipher block chaining message authentication code. So this is also referred as authenticated encryption mode. Authentication encryption is a term used to describe encryption system that simultaneously protect confidentiality and authenticity of communication. So authentication encryption is nothing but main aim here is you have to protect, you have to see that the confidentiality of information has been highlighted, and authenticity, that is integrity, that you have seen that whatever the message has come from the authorized person is of the genuine person, not with any hacker or any man in the middle attack has not occurred over here. So this mode of operation, that is a confidentiality and authenticity mode of operation, provides both forms of securities. So same mode of operation provides the confidentiality and authenticity security concept to the messages. So here we are going to use a single key is used for both encryption and for the MAC algorithm to create a MAC code. So the CCM encryption process consists of 3 elements. First is data will be both authenticated and encrypted, and that we are going to call it as a plain text. The second element is associated data. So that will be encrypted but not authenticated. A nonce n that is assigned to payload and associated data. This is a unique value to prevent a replay attack. So all these 3 elements are being used for this encryption authentication process. So in this mode of operation, we are going to satisfy both, that is confidentiality and authenticity. So to provide those two events, to provide those two confidentiality and authenticity, we are going to use the 3 elements over here: plain text, associated data, and the nonce. Plain text is your normal information, and your associated data that will be encrypted, but it is not an authenticated part. It is an information for which you are going to give authentication over it. And a nonce, it's just a unique value which has been used only once for each and every part of your information wherever you're going to have a transaction over. So in the case of authentication, all these 3 information, the nonce, authentication data, association data, plain text, are combined and being divided into different block size. So each block is given to an encryption algorithm, that is the CMAC algorithm with the key value, and you're going to produce a tag over here. This tag indicates that it is of the authorized person. If the same process goes on at the receiving end, and whatever they get the tag and what they have received the tag, if it was of the same part, then they come to conclusion that the plain text is not altered. And we can make sure that the B0 is almost all your nonce value, and B1 and B2 can be your value of associated data, and remaining information is absolutely of your plain text information. All these will be encrypted with the key value, and you're going to produce the tag value. Then coming to the encryption part, that is your confidential part. Your plain text is being given to a control, that is you will be having different control unit with the key value. It processes the ciphertext, and then it is going to attach to your tag value. So that is nothing but your authentication tag value. This has been got by using a control value, is being encrypted with the key value. This key length value is being XORed with the tag which you have got in the previous section. That is this. The tag what you have got in the authentication part is been encrypted with the ciphertext, which has been encrypted with the control part of it. And then this tag is been attached to your plain text, which satisfy the first half of your plain text is of the confidential part, and the second part gives you the authenticity part. So a combination of these things will be transmitted to the destination, and the destination will verify by taking this particular MAC code to cross-verify whether your plain text has been altered or not. So the next topic is public key cryptography. Before going to the public key, traditionally the private or the secret or single key cryptography uses only one key. So shared, and this key has been shared by both the sender and the receiver using only one key, and that key has been called as a private, or you can call it as a secret, or you can call it as a single key. It will be shared with both sender and the receiver, and you're going to have a concept of encryption over here. So if this key is disclosed, that is, if the key is known to any other hacker, then your message will not be of the confidential part. So you have to compromise with the security section. So it is also called as symmetric. So parties are equal. That is, both the users should know the secret key, what they have used for the encryption part. Hence, does not protect sender from receiver forging a message and claiming is sent by the sender. That is, you have to concentrate more on the secret key such that if any third person takes the key and encrypts and say that I'm only the authorized person, you can't have any guarantee of cross-verifying whether he is of the authorized person or not. So protection given to the key is more important over here. So whereas in the public key cryptography, probably most significantly advanced the 3000 years history of cryptography. It now, like, we are using the two keys. One key will be called as a public and the other key we call it as a private key. So it is also called as an asymmetric since parties are not equals. That is, two keys, whatever you're going to use for encryption and decryption, are not of the same key. So it uses the clever applications of number theoretical concept of function. That is, we are going to generate a key in such a way that if one key is being used for locking purpose, obviously by having a new number theoretical concept which is being calculated for the generation of the key, the other key will be used for decrypting the information. So randomly, I can't take any two values and I can't say that these two are the public and the private key. I have to tally it. I have to cross verify. I have to mix it up with a theoretical concept to function such that if one key is used for the encryption, the other key has to be decrypted with a concept over there. So complements rather than replacing the private key cryptography. That is, we have a great security over here by implementing the two keys over here such that no man in the middle attacks occur. So why public key cryptography? So it was developed to address mainly the two key issues. So one is the key distribution, the other is the digital signature. So key distribution is nothing but I have to distribute the key, which was using in the symmetric encryption algorithm. As we had a single key, and the single key has to be used in the sender as well as at the receiver end. And as the receiver has to use the same key for decrypting and get back the information, the key has to be distributed. The key distribution can be done in two ways. One is I can share the information, that is, I can share the key in somehow that I can secure that no other third person come in the middle. I can give lots of encryption concept to the key itself and transmit the information, or I can give them some code value. I can give some mathematical concept such that once I get the resultant of the mathematical operation, that will be the final key value. Or through person, I can hand over the key value such that the information will be secured, which will not be leaked out to the third person. This is one way. And the second way is using the concept of key distribution center. That is, I'm going to depend on the network itself such that those people will securely transmit the key value to the destination. Either in the two ways, I have to transmit the key value to the destination. And the second is the digital signature. You have to verify a message comes intact from the claimed sender. I'm going to sign and I'm going to encrypt the information. I'm going to lock the information such that my signature will not be identified or will not be copied by any other person. Only the receiver will be able to know that he is of the authorized person by identifying my signature, and they can consider the information as a valid information. So public key cryptography was published by the Whitefield Diffie and Martin Hellman at Stanford University in the year 1976. It was the first proposed by Diffie and Hellman, and it is based on the mathematical function rather than on simple basic operations on bit pattern, such as we are used in the symmetric encryption algorithm. So the operation also differs totally over here. We are using mathematical operation, not a simple bit pattern of operation we are not going to use over here. So there is a pictorial representation which explains the encryption with the public key concept. So this is my plain text. My plain text has been given to an encryption algorithm. Encryption algorithm can be selected with lots of encryption algorithm. Any one algorithm I can select it. The same algorithm should be used by the receiver to decrypt the information such that they get back the same plain text over there. So based on selection of the encryption algorithm, I'm going to select a key over here. So as I'm going to send information to the Alice, I'm going to take the Alice public. So these are the public keys of different users, that is Job, Mike, Alice, and Ted, which all the public key are stored in a common shared area. So to whomever I want to send any information, so those public key I can consider, I can take the public key, I can encrypt it, and then I can transmit to the destination. So public key will be known to everyone, such that anyone whoever wants to have a transactions, those public key can be considered and they can transmit over them. So in this example, as we are transmitting to the Alice, Alice public keys will be taken and it will be encrypted. The ciphertext will be transmitted to the destination. At the destination, as the ciphertext has been received at the receiver side, the Alice will use its private key, which has not been shared. So that private key will try to unlock your ciphertext and get back to your plain text over here. So now sharing of the public key can be done in a different way. So this public key can be shared, can be kept in a common shared area such that anyone can use, or I can use a PGP concept and I can share the public key, or whoever wants to have a transaction, for them I can send separately the public key to them and then have a transaction, saves a transaction with the receiver and the destination over here. So the concept says here is public key will be known to everyone. With the help of their own public key, we are going to encrypt the message, the plain text, using different encryption algorithm and transmit the ciphertext to the destination. At the destination, the same decryption algorithm should be used with their own private key. They're going to decrypt the information, get back their plain text over here. So this public key encryption scheme has 6 ingredients. First is plain text, which is a readable message or the data which is fed into your algorithm as an input. The second is an encryption algorithm, which performs various transformation of the plain text. That is, a mathematical operation will be done on the plain text to find out the ciphertext. Third, public and private key. You're going to use a key over here. A pair of key is selected so that if one is used for encryption, the other is used for the decryption. I'm going to decide whether I have to use a public key as for decryption part or the private key for the decryption part. Depending on my consideration requirements, I'm going to decide which key will be given as a global over there, as a considering as a public key. So the exact transformation performed by algorithm depends on the public or the private key that is provided as an input over here. And the ciphertext is nothing but a scrabbled information or message which has been produced or considered as an output. It depends on the plain text and the key value. For a given message, 2 different key will produce 2 different ciphertext over here. And the last, the decryption algorithm, which accepts the ciphertext as an input and matching the key value produces the original plain text over here. The same thing is being given over here. This is your plain text, the first. The second is your encryption algorithm. The third is your public and the private key. This is your public key and this is your private key. Fourth, your ciphertext, which have been explained in the mathematical format as y is equals to E of PUA, comma X, where X is your plain text, PU is your public key of the Alice, and E is an encryption algorithm. When you execute this particular section, you're going to form a Y, which is your ciphertext. At the receiver side, you're going to X as a plain text, you're going to get back your plain text X by using a decryption algorithm of the private key of Alice with the ciphertext over here. So requirements of public key cryptography. So it is computationally easy for a party B to generate a pair of key. Either it can be a public or the private pair of key. The second requirement says that it is computationally easy for sender A, knowing the public key and the message, to be encrypted M to generate a ciphertext. So even this is also very easy for sender A. So he'll be knowing the public key as it has been shared to everyone, and the message of its own will be encrypted to generate a ciphertext. So that has been explained in the mathematical form as C is equals to encryption with the public key of your message. B is a destination part. The destination's public key you're going to consider with the message. You're going to have an encryption algorithm for that and produce a ciphertext. And the third, it is also computationally easy for the receiver B to decrypt the resulting ciphertext using the private key of its own to recover the original message. So even for the receiver also, it is very easy to get back the plain text by using the same decryption algorithm as well as their own private key. That has been given in a mathematical form as message is equals to, you can get back your plain text message by implementing the decryption algorithm of the private key of its own with your ciphertext. Ciphertext is nothing but encryption of the public key of its B part, B is a receiver, with your plain text M. So it has been expanded. This D of PR B, C has been expanded as D of PR, that is private key of its B function, B receiver, which has been encrypted with the public key of its own and with the plain text over here. And the next requirement will say that it is computationally infeasible for any opponent knowing the public key to determine the private key. It's very difficult. By knowing only the public key, I can't consider, I can't determine, I can't find out what may be the private key. So the next step, it is computationally infeasible for an opponent knowing the public key and the ciphertext to recover the message. And it's also very difficult for any third person to identify the message, to recover back the message by knowing only the public key and the ciphertext. By having these two information, it's very difficult to recover back the plain text. And the sixth requirement, which is an additional part of it, either two related keys can be used for encryption with the other used for the decryption. So here they say that any one I can consider for encryption and the other for the decryption. That has been given as in the mathematical format as M is equals to, I'm going to use a decryption algorithm with a public key and a ciphertext over here. Or I can decrypt an algorithm with a private key with the ciphertext over here. So that ciphertext can be encrypted with a plain text message with the private key of its own, or I can have an encryption algorithm with the plain text message with the public key of the receiver. So any one concept I can use over here. So one concept will be considered the public key which has been shared, and using the public key I'm going to encrypt the information. This can be of your confidential part of it, which gives you the confidential, says that anyone can be encrypted your message, only the authorized person will decrypt the information. Whereas this will provide the concept of the digital signature, where it's saying that only the private key, only he can send the information with its own private key, locking with it such that no other can imitate its signature and no other can transfer the information with that. Only the public key can open the information, can be viewed by anyone. So these two are the concept where you can use the key can be implemented either in the encryption part of the public key or with the private key. So there is a differences between a conventional encryption and the public key encryption. So first is the same algorithm with the same key is used for encryption and decryption. So we are not going to use two different keys. Whereas in the public key encryption, we are going to use one for the encryption and the other for the decryption. And those two keys are paired to each other before declaring it as a public or the private. The second difference is the sender and the receiver must share the algorithm and the key. Both has to be shared among themselves. Whereas in the public key encryption, the sender and the receiver must each have one of the matched pair of the key. Obviously, and the algorithm also should be known to each other such that the same decryption algorithm will be used by them. Considering the security section part of it, the key must be kept secured over here, whereas at the public key, one of the two keys must be kept secure. One can be declared as public, anyone can use by it. Second, it must be impossible or at least impractical to decipher a message if no other information is available. It must be impossible or at least impractical to decipher a message if no other information is says that without any key value, it is impossible for any message to decrypt the plain text. So, concerned with the symmetric and the public key part of it, both the key value has to be saved. Either in this conventional, we are going to consider only a single key, whereas in the public key, we are going to consider two keys also. One key will be kept it as a secret key for which we are going to find the ciphertext of it. And the third, knowledge of the algorithm plus the sample of the ciphertext must be insufficient to determine the key. So whereas here, the knowledge of the algorithm plus one of the key plus sample of the ciphertext must be insufficient to determine the other keys. That is, to identify the key, the algorithm and the ciphertext should not depend on what may be the key value. So it should be an independent such that it should not be very easy to guess based on the algorithm and the ciphertext. Whereas in the public key, apart from the algorithm and the ciphertext, with the help of the public key also, it should be very difficult to identify what may be the private key of it. So these are the differences between the conventional and the public key encryption. For this, we'll stop the topic today.